So, okay, while we wait for the boat to dry, do a small exercise. So you had the expression for d gamma dE in the limit neutrino mass is 0. Now, and that expression depended on, of course, this constant G and electron mass ME and the energy transfer from, or rather the mass difference between the initial and final nucleus Q. Now, let's make a assumption that this value of Q is much larger than ME. ME is 0.5 MeV, and let us assume that Q is some 50 MeV. There are transitions where such large Qs are possible. So, in such a situation, I can approximate the total gamma. In calculating total gamma, I can make the approximation of neglecting ME. The integ I have d gamma dE something. So, and in order to get gamma, I have to integrate dE goes from ME to Q. But I extend the lower limit to 0. That is one approximation I will make. And second approximation I will make is within the integrand also, I expect that effect of ME has only a negligible role to play. So make that approximation and evaluate gamma. It's a very simple integral, but there is something to be learned from it. So set ME equal to 0 in the expression for d gamma dE and integrate it from 0 to Q. Let them take 2-3 minutes to finish that small exercise, because there is something one needs to understand by doing that exercise. So it goes as g square q raised to the power 5. And what we have calculated is gamma. Because in usual language, gamma has dimensions second inverse. It's the rate at which decay is taking place. But in energy units, this has in electron volts or keV, meV, etc. Because we have E is equal to h nu. Nu and gamma have the same units. And this is some numerical constant times g square q power 5. And q, of course, is the mass difference, so that also has dimensions of energy. So, what are the dimensions of G? Of G, not G square. and if you measure the value of G, you get some number, and it is easy to remember in the following way: G times mp square is 10 to the minus 5, and if you approximate proton mass is actually 0.938 GeV, but if you approximate it as 1, then G is 10 to the minus 5 GeV power minus 2. The fact that this coupling constant has negative energy dimensions, it has some very important consequences in field theory. In field theory, you are allowed to have dimensionless coupling constants and maybe coupling constant with a single power of energy going like energy, but you are not allowed to have any other coupling constant if you want what is called a renormalizable field theory. And the fact that this Fermi coupling constant has negative power of energy implies Fermi theory is not renormalizable. It works at the scale, that is at the scale of maybe few MeV to tens of MeV. It works at that scale, but if you try to use it at a higher energy scales, it may not work. So now let us look at the relativistic form of Fermi theory. By the way, have all of you done a particle physics course last semester? You also? You have not done. So you need to know some very essential basic facts about quantum field theory. There you represent a fermion by a field psi, which is a function of space and time. This x indicates both spatial coordinate and time coordinate. And this field can do two things, rather it can do one of two things. It can, if this field represents an electron, for example, it annihilates an electron or creates a positron, that is the antiparticle of electron. And related to this field psi, we define a psi bar. By the way, do you understand the phrase Hermitian conjugate? I mean, you are familiar with matrices. So, we think of psi of x as a column matrix. So, I can take its transpose, then I think of it as a row. In addition to taking transpose, I also take complex conjugate, because this psi consists of a column of complex numbers. So I take transpose, get a row of complex numbers, and take complex conjugate of those complex numbers. So this double operation, transpose complex conjugation, is called Hermitian conjugation. And here this psi bar is the Hermitian conjugation plus an additional operation which is related to the spin of electron, and if I go into those details it will take just too much time, but you can take it that this is related to this through complex conjugation, and complex conjugation means you replace particles by antiparticles and antiparticles by particles. So the psi bar creates an electron and annihilates a positron. And one very important point is any interaction I write down, it's part of a Lagrangian, and Lagrangian has to be invariant under Lorentz transformations. So the interaction should have terms which go like psi bar psi. We can show that this quantity is invariant under Lorentz transformations. Now let us look at quantum electrodynamics, which was the basics of quantum electrodynamics were developed between 1928 to about 1930 or so, which describes the interaction between electrons and photons, and that interaction is of the form some coupling constant E times psi bar gamma alpha psi A alpha. I can show that this psi bar gamma alpha psi transforms as a 4 vector, and I dot it with another 4 vector so that I get a Lorentz scale. One important detail I should emphasize: psi bar x gamma alpha psi x A alpha of x. The 3 fields psi bar, psi and A, all 3 fields have exactly the same space-time coordinate. So interaction is taking place at a single point. The slightly more technical language is interaction is local. If there is something here, it cannot affect something far away from it directly. If it is to affect it, for example, if I sort of wave my hand here, in principle, you shouldn't feel any effect. But of course, if there is lot of, imagine we are all submerged in a pool, and if I wave my hand, I create a wave, that wave will travel, and then you feel the pressure due to the wave. So, but there is no instantaneous connection between 2 points separated from each other. That is the whole point about quantum field theory. Interactions have to be local. Then, based on which, let us look at the scattering of 2 electrons. So here is where we use this concept of Feynman diagrams. I draw a black box. And my time is flowing upwards. So there is an electron going in. This has momentum P1, this has momentum P2, this has momentum P3. So there is an electron with momentum P1 going in, and there is an electron with momentum P2 going in. And there is an electron with momentum P3 going out, and another electron with momentum P4 going out. What is happening within the black box, I don't actually see. Now, based on this hypothesis that interactions are local and they are of this form, what are the possibilities? Possibility is this P1 electron is connecting to P3 electron and a photon is emitted. And that is connecting here. So you see what is happening. The P1 electron is annihilated at this point, and at the same point the P3 electron is created and a photon is created. This is at point x1, and at this point x2 the photon meets the other electron. So the P2 electron is annihilated, P4 electron is annihilated, and the photon is also annihilated. And this field A alpha is capable of both creating a photon as well as annihilating a photon. So, according to the rules of quantum field theory, I describe this interaction in this manner, that at point x1 at time t1, the P1 electron emitted a photon, and at point x2 t2, the P2 electron absorbed it. But what if the time t2 is earlier than t1? That's a possibility. I consider that and I add that also. But if you look at more closely, there are other possibilities. Outside the black box, things look exactly the same. But it's entirely possible that this P1 electron joins the P4 electron. Nothing to stop it. And the P2 electron joins the P3 electron. And of course, there is again a photon exchange at some point y1 and y2. So, and this is the famous progress made by Feynman, that he showed that if I add the two amplitudes, one where photon is emitted at x1 and absorbed at x2, and the other amplitude where photon is emitted at x2 and absorbed at x1, if I add the two amplitudes, I get a relativistically invariant amplitude. This is the famous result of Feynman. And same thing here also. So I get a relativistically invariant amplitude here. I get a relativistically invariant amplitude here. And I add the two amplitudes in a manner consistent with rules of quantum field theory, and which eventually means that there is a relative minus sign between these two, because in some sense I am interchanging these two fermions, and according to the rules of quantum field theory, if you interchange two fermions, there is a relative negative sign. So let us write down the amplitude of this using that interaction. So I have the coupling constant E times this P3 fermion is being created. So I have psi bar P3 gamma alpha, and this P1 fermion is being annihilated. So psi P1, and similarly here there is a coupling constant E. P4 fermion is being created, and here I put gamma beta because this is independent from this. And I have this internal line. This is a rule in Feynman diagrams. The internal line, at least from the theory point of view, it is as real as you can imagine, but you can never see it in an experiment. And that is the probability of a photon being emitted here, absorbed here, plus photon being emitted here and absorbed here. And if you add those two, you get G alpha beta by Q photon square. By this I mean energy square minus momentum square. That's what this is. So this is E square by Q square photon times psi bar P3 gamma alpha psi P1 psi bar P4 gamma alpha psi P. That is how this amplitude looks, and this amplitude essentially has the same form. It's just rearrangement of terms, and of course the Q photon here will be different, but the basic structure will exactly be the same. So this is how a QED amplitude looks, and Fermi of course wanted a theory which satisfies all the rules of quantum field theory. So he wrote down the following interaction Hamiltonian. First, let us draw a block box for β-Decay. By 1934, a neutron was discovered, and people realized that a β-Decay can be thought of as a neutron in the nucleus. Effectively, a neutron in the nucleus is transforming into a proton. So I have a neutron going in, and I have a proton coming out, and I have an electron coming out, and I have something else coming out. I will not put a. This is what you see, and Fermi wanted to write an interaction Hamiltonian for this object. So I use the same rules as above. So there is a neutron going in and disappearing. So there should be a psi-n field which annihilates a neutron. And there is a proton coming out. So there should be a psi bar p field which creates a proton. And there is an electron which is appearing. So there should be a psi bar e field which creates an electron. Now I am left with this. How do I describe the creation of this? Remember the rule of quantum field theory. Whatever I write down should be Lorentz invariant, which means the only option I have is to put a psi field, not a psi bar field. So I put a psi nu field. And Fermi construct, what do I put between psi bar and psi bar p and psi n, and what do I put between psi bar e and psi nu? Well, in principle I can put one here and one here also. But Fermi was trying to use QED as an analogy. So he put gamma alpha and gamma alpha here. And you have to put a coupling constant in front, which he called G. And now you compare this and this and ask, what are the dimensions of G? It has same dimensions as E squared by Q squared photon. And E is dimensionless and Q squared photon has dimensions energy power minus 2. So the Fermi coupling constant has dimension energy power minus 2. Another way of looking at it is if you study Maxwell theory, the quantized version of Maxwell theory, that is quantized version of electromagnetism, that is theory of photons, you will see that photon field should have dimension of energy. And if you study Dirac theory of electrons, you would see that the Dirac field has dimension, energy dimension 3 by 2. So psi bar psi has dimension 3, A plus 1 has dimension 4, and terms in Lagrangian should have dimension 4, so that action is dimensionless. So E is dimensionless. And according to the same argument, I have psi bar C, psi bar psi dimension 3, another psi bar psi dimension 6 divided by 2. So effective dimension 4. So this effective electron-electron interaction also has dimension 4. And same thing here, psi bar psi dimension 3, psi bar psi dimension 3, 6, and this is dimension minus 2, so effective dimension 4. By the way, why did Fermi put psi bar p psi n? Why not psi bar e psi n? If we are just applying rules of quantum field theory, in principle one could have written that also. But if you write that theory and compare it with experiment, it doesn't match. So we use this choice rather than the other choice. That is one way of thinking. But also look at it from sort of quote common sense point of view. The mass of neutron and mass of proton are very close to each other. They match to 1 part in 1,000. Whereas mass of electron is 2,000 times less. So if neutron is converting into something, it makes more sense that it converts into proton than into electron. That is a sort of common sense hand-waving point of view, but which is also borne out by experiment. So this is the Hamiltonian Fermi wrote down, and he applied the rules of quantum field theory. There is the famous Fermi golden rule of quantum field theory, which again is final state H, initial state mod square delta E final or usually it is written in terms of a 4-dimensional delta function. At least the people who have done the particle physics course, I hope you have seen this formula. So you apply this formula and you get exactly the same result that we got in a simple-minded way using the non-relativistic theory. And I mentioned this in the last class. So you have, from this formula, you calculate d gamma dEE, compare the shape of it to all the experimental data that is available, and you get a good match. By the way, there are corrections involved because I have, let's say, a uranium nucleus which has 92 protons in it, and an electron is emitted. Uranium undergoes β-decay and an electron is emitted. Obviously, these 92 protons exercise a powerful electrostatic force on this electron. So, and the electron has to sort of come out of the potential well created by these 92 protons. So, if you look at the β-decay of a uranium, it will not actually directly match with Fermi formula, but if you apply the corrections due to this electrostatic force, you get a good match. So you have to keep this in account, keep this in mind. But Fermi theory, the predictions of d gamma dEE by Fermi theory match the experimental results, and as I mentioned before, you calculate gamma using Fermi theory, compare it with the measured value of gamma, and that gives you the value of G. However, there is a very serious problem which developed. a typical nuclear decay, we write now you see I put a bar. Oh, sorry. Before I describe the problem, I need to answer your question. So let me answer this. So the rules of quantum field theory, which demand that interaction should be a scalar, force me to write a sign nu. But this sign nu, I want it to create something. So what it is creating is an antiparticle. So that is why I write a nu bar. But the rules of quantum field theory, creation of nu bar is equivalent to annihilation of a neutrino. So in drawing the Feynman diagrams, we put the arrow along the fermion direction, not along the momentum direction. So this is how we write the Feynman diagram. Now, compare this diagram with that diagram. It's sort of very tempting to write a connecting particle between at this place where the neutron is getting converted into proton and this vertex where the electron and neutrino are being created. So let us sort of close our eyes and write such a particle. But you see, neutron is turning into a proton. Charge of neutron and proton are different. So this particle must have electric charge. And when Fermi wrote his theory, nobody had any idea about how to construct a quantum field theory of a vector particle carrying electric charge. That's problem number 1. And problem number 2, if I put a particle like this, I should have a propagator, and the propagator should depend on the kinematical details. So answer to that is, let this particle have mass m, in which case so if I have a particle with mass m and carrying momentum q, vector particle, so indices alpha, beta, its propagator. There are other corrections to it, but its propagator should roughly go like this. And if you argue that the values of q square that you consider are much less than m square, then this becomes just, which is a constant. So I justify that the Fermi coupling constant being a constant. That yes, if I consider energy transfers comparable to m, then I have to worry about the kinematical details. But if I consider energy transfers of the order of MeV or even tens of MeV, then those are much smaller than the mass of this particle. Therefore, I don't have to worry about it. And I make this approximation, which means that whatever is sitting in front is a constant, and which gives rise to Fermi constant. So that was the argument made, but two severe problems. Problem number one, how does this mass come about? People didn't have any idea. And how to construct the quantum field theory of a charged vector particle. Because it carries electric charge, it should couple to photon. And how to construct charged vector particle which couples to a photon appropriately. That was a very complicated issue. Certainly in 1930s, nobody had any idea about it. But in 1950s, this coupling of a charged vector particle to photon was solved by introducing what is called non-abelian gauge theories. And in 1960s, problem of giving mass to such particles is also solved through what is called Higgs mechanism. And Higgs mechanism predicts that at the end of the day, there will be a scalar boson in the theory. And after half a century of struggle, in 2012, that scalar boson called Higgs boson was discovered at CERN. So it's a whole big story. We will not go into any further details. But this is how we get what is called the 4 Fermi interaction. So I take this Feynman diagram and I make this approximation. So I draw a wavy line as long as q square and m are comparable or q square is much larger than m. But in the limit q square is much less than m, I collapse this wavy line into a single point. So this is point x1 and this is point x2. And I must have visible momentum to sort of distinguish x1 and x2. But if the momentum is so small, I can't distinguish between x1 and x2. I practically consider them to be the same point. So we say that all the 4 fermions are interacting at a single point. So if I can replace the propagator by a constant, that is equivalent to saying that the two points where the interaction are taking place, they are so close that I essentially consider them to be the same point. Therefore, I write it like this, and this is what we call 4 fermion interaction. But you should always remember that 4 fermion interaction is an effective interaction, and if you go to high enough energies, you should actually consider that. Yeah.
At higher energy, the propagator came into the picture. I mean, it must have charge. So but why mass? Can it be massless but charged?
Such, in principle, quantum field theory allows such particles, but unless it has mass, I cannot make this approximation. I mean, Fermi constant is a constant. It is independent of the momentum transfer that is taking place in beta decays. Which means that it has to be massive and the mass has to be so large that the energy transfer taking place in beta decay can be neglected.
Why 4 4 fermion interaction is required, is not allowed by theory. I mean, why do they?
Because 4 Fermi interaction has a negative coupling constant of negative energy dimension. And if you have a coupling constant of negative energy dimension, your theory is not renormalizable. So that's why we use it to describe data in a particular energy region. But we insist on renormalizability because we want the theory to work from very low energies to very high energies. If we insist on such a theory, we have to impose the condition of renormalizability, and renormalizability forbids couplings with negative energy dimensions.
Can I say that it's negative energy dimension coupling because all 4 fermion interactions will be negative?
If any 4 fermion interaction you write
Is not allowed.
It will necessarily have negative energy coupling, rather negative energy dimensional coupling, and such couplings are not renormalizable.
There's one more question. What about like more point, like 5 fermion interaction, something else?
No, you can't write 5 fermion interaction because it will not be invariant under Lorentz transformations, but I can write 6 fermion interaction. Effective 6 fermion interaction I can write.
Which are renormalizable?
Which are not renormalizable because then it will have energy dimension -5. By the way, what's the time? Okay, I have to go now, so I will stop. But important point is Fermi theory is incomplete. I grandly told you that it describes all weak interactions, but all beta decays, but it doesn't. Why? I will explain in Saturday's class, and I will explain about 2 changes that were made in Fermi theory. One by Gamow-Teller, and one is called V-A. I will describe them in the next class. Okay, so we'll meet at 4 o'clock on Saturday.